Good morning. Thank you all for being here. My name is Daniel Sanchez. I'm a research associate at the University of Bonn. And today I'm going to talk about the approaches that we're taking to calibrate an X-band radar network in Western Germany. I would like to acknowledge my colleague, Silke Trömel, but also all the members of the radar group at the University of Bonn. So, this project is part of a larger project. You can see this really big German word that I won't dare to mispronounce, but it's part of a bigger project. And the main goal is to provide high quality QP products and nowcast. So to this end, we must monitor the calibration of local polarimetric X-band radars. One is located in Bonn, namely Boxpol, and the other one is located in Jülich, Joxpol. So the talk outline, we have this assemble of several approaches to keep the calibration to monitor the calibration of the radar network. I'm going to describe why we implemented these methods, how are we implementing these methods, the data that we're using on each piece of this big assemble. But I also would like to focus on the big challenges that we overcome, but also which challenges still remain that to keep all the radars working. So each X-band radar covers up to 150 kilometers at 10 different elevation angles. And you can see in yellow, it's a Boxpol, in blue is Joxpol, and they are within the range of the DWD C-band radar network. So yeah, the radar processing chain that we're using. The first piece is the ρHB correction. So the ρHB correction, this method, it's a method described by Ryzhkov and Cernik, and it consists on varying the radar constant in this here we have to vary the radar constant to reach a flat dependence of ρHB on SNR. So our method, it's basically this application of this approach until we reach a value that we can see that it's less noise and a flat dependency. In this case, when we correct our ρHB, these are the results. So this is the raw ρHB. And here you can see that we like the values increases on ρHB. However, we consider that the key challenges for this approach were not to overcorrect ρHB, because sometimes this approach tends to generate values of ρHB below above I don't know, in range like 1.2 or something like that. So our method is keeping this thing monitored. It's do not overcorrect the ρHB, but it's also really computationally cheap. The next piece of our chain is the unfolding of FDP. It's based on the standard deviation of FDP, the FDP slope and ρHB, as proposed by Wang et al. And you can see as an X-band radar, we have a lot of folding on FDP. So in this region, in the color scale, you can see that it changes. It's there's a sweep over there. So yeah, we're correcting also a FDP for unfolding. And the next piece is the clutter ID. This method is the identification of clutter of all non-meteorological echoes. It's based on the study proposed by Rico Ramirez and Clocky, and it's designed to classify non-meteorological echoes. So we're identifying ground clutter, sea clutter, or an anomalous propagation. So in this case, the challenges were to create this empirical probability density functions, but also these clutter maps that are built using dry day scans, so days with no rain at all. So when we generate these membership functions and the dynamic clutter map, these are the results of the clutter identification. You can see that even with a strong rain, we're identifying the clutter. So yeah, these were the key challenges to compute the membership functions and to identify in time and space the scans with no rain. Another step is the detection of the offset on ZTR and on FDP. So this is based on the traditional method where we have the verbal scans, we have the PPIs taken at vertical incidence. We average to build the vertical profiles, and then we set these thresholds related to light rain. So we make sure that it contains 2 or more consecutive bins of ZDR in the rain region and corresponding values of ZH and ρHV that make sure that we're really in rain. Same for FDP. It basically is the same method in ZTR. Some people may argue that not the offset on FDP is not that important, but I think that you have to find the offset on ZTR, on FDP, sorry. So in this case, we have 5 years of ZTR offset and FDP offset, and yeah, it's the method. It's quite stable, especially in the boxpole radar side. You can see that especially one thing that is bothering us is like there is this seasonal dependency here on ZTR, here and here. But yeah, the method it's working well finding the offset. However, on the boxpole radar side, we're having this. At 2021, starting 2022, we had this big variation on ZTR calibration. And yeah, you can see here, even on FDP was quite stable, but then it became really noisy. So the reason for this is you can see in boxpole, we're starting to see this enhancement that are introducing several errors on the radar side. Here, the key challenges are to the detection of the melting layer. So the melting layer, we are detecting the melting layer using the vertical profiles, but also using range defined QBPs. So we have like this backup method from RDQBPs, where we're detecting both the top and bottom of the melting layer. But a challenge that still remains is how can we detect these spurious echoes that we can, so we can make sure that ZTR is usable for QP, for generate QPE. The next step in our chain is the attenuation correction. The attenuation correction is based on the method proposed by Rico Ramirez, and it's we have to optimize the parameter B and alpha on these equations, and you can see in this example that there was a lot of attenuation on the horizontal reflectivity. So here you can see that this event is related to the flooding, big flooding event in Germany in 2021. And you can see here that we had attenuation close to 20 or 30 dBz. So, however, the key challenges for this method is that it assumes an isotropic melting layer. So you can see here in the horizontal attenuation that we're assuming an isotropic melting layer. So this could maybe be a challenge. However, I think that the method works really well to correct for attenuation. We're also correcting for differential attenuation. We're using exactly the method, kind of the same method, optimizing the parameter gamma. And the next step is the computation of KDP. So we're computing KDP using two methods, the one proposed by Vulpiani, but also one in X-band radars. It's you can see in this equation, the parameter C is close to unity for X-band radars. So we can generate two KDPs. This KDP that it's results from the processing of VDP and the smoothing, and this one that it's a little bit with more high resolution. So these two KDPs are really reliable, and they really match. The next step is the calibration of ZH, and we're monitoring the calibration of the horizontal reflectivity with this approach that it's a combination of the relative calibration adjustment technique proposed by Silverstein et al. And a method proposed by Diederich et al. So the combination of this method, it's the basis of the RCI technique is that any variation in ground clutter is caused by a change in radar calibration constant. So what we you can see in this equation, it's we have to determine a baseline for the clutter reflectivity distribution. In this equation, what we're trying to do is this baseline, we are trying to compute it for the Diederich method. So in the RCA method, we have to compute the 95th percentile of the ground clutter reflectivity distribution. And then we're trying to combine with a method proposed by Diederich that it compares the reflectivity at horizontal polarization derived from specific attenuation with reflectivity corrected for attenuation. However, this method, it's a little bit difficult to implement because it requires big events with attenuation. So you can see here, we have a row ZH. We identify the clutter. And after all, we set these thresholds to keep the RCI technique. So we have clutter pixels within a range of 10 kilometers. We have a frequency map pixel that all these pixels has to be bigger than 80% on the clutter probability map. And the values of the horizontal reflectivity has to be greater than 40 dBz. So here are, again, 5 years of the monitoring of the RCI method. Here, again, we have this seasonal dependency. I don't know, I'm not sure why we're seeing a seasonal dependency on clutter values, but that's in the box-pole radar side. We have, maybe it's because we don't have a radon, but in the Jox-pole, it's much more stable. So it's working really good, especially on that radar. And yeah, the same on the calibration of, so we have this value of ZH corrected for attenuation. We have the attenuation that we're computing it from this equation that it was derived using DSD simulations. And you can see here that we can see a little bit of values that are where we can detect the partial beam blockage, but all the other values, when we take the difference, they are related to the bias in the reflectivity. So these are the results for the method. We're seeing, you can see, we can detect the partial beam blockage, the values of the offset in ZH. However, we're still struggling to find a proper averaging over a sufficiently large spatial and temporal domain to mitigate the effect of the DSD variability. And we also have to find a proper thresholds to mitigate the influence of backscatter differential phase shift and light rain. So to sum up, we are monitoring with robust polarimetric-based techniques the calibration of 2 X-band radars, and combining the RCA method with a method that computes ZH for attenuation, it's showing encouraging results. This could enable us to monitor the calibration of the radar reflectivity based only on data collected by the radar itself. However, future work will focus on the validation of the radar QPE And finally, all these methods are available in open source tools such as TowerPy and Radlib, so you can modify all your parameters and you can replicate our methods. So that's it. Thank you very much. Questions?
Check your first calibration that you are detecting the melting level at the height. So if I understood correctly that you're saying that the values above it are not valid, or why do you want to detect it? Offset your offset calibration.
No, it's below the melting layer, so in light rain. Because if we are sticking below, maybe nice, we're not seeing really good results. I think it's a little bit much more stable if we stay in light rain.
Okay. So you check that it's not the system dependent bias actually in the lowest elevations. So if you have a stronger precipitation, then you can use also lower levels.
No, it has to be in light rain. So the thresholds are like below 30 dBz. Then if we have a convective events or more strong rain events, it's more difficult to estimate the ZZR offset.
Yeah, well, if you like, we have C-band radars and you never check X-band, but anyway, if you rotate an average in over 360, it doesn't matter that much what is the rain intensity, because the droplets move around anyway, more or less, and then if you rotate, because even in when there's snow or ice crystals, the results are really good if you just integrate it over 360. I'm a little bit puzzled about it.
Yeah, but sometimes I agree with that, but then you have a little bit of a greater values, then they tend to make more difficult to have a really valid values, because then when you combine with a ROHB trying to detect this rain region, it's a little bit difficult to find where is the really the end of the start of the melting layer. So it's better to stick at maybe a light rain. It's a little bit more robust, I think.
Having the calibration adjustment. In Switzerland, we now have 5 C-band radar, but a long time series was the 3 quartiles, 25, 80, and 75, 90, and 95. And according to our experience, the 95 is definitely, as you could expect, the more volatile, the one that varies the most. So have you tried other, maybe a smaller thresholds?
Yeah, we tried on even on the 15th percentile, but I think that this one for us it proves to be the more stable one, at least in our results. I think this one, at least for something that changes for me a little bit more. Sometimes it's the so we have to be like close to the radar. In our case, it's 10 kilometers. But if you change this value of ZH above 40 dBz, that parameter is the one that produces more different results. And that's the one that affects the most.
was thinking about possible explanation for the seasonal dependence observed on the
Yep.
stroke. Have you looked for correlation with the receiver temperature? I believe that since that one is the radar that doesn't have rating, right?
Yeah.
So, LNA, the low noise amplifier, are quite dependent on the temperature regarding the stability.
Yeah, and then we're seeing this seasonal dependency even on the ZTR offset, but also on clutter values. So here we have exactly the same seasonal dependency. I mean, maybe this part is like for some other technical issues on the radar for the radar technicians, and I'm not sure why this could be happening. But yeah, maybe what you're saying it's maybe the answer, because we're seeing this seasonal dependency, but why is on the clutter also on the clutter values? That's our main question.